In example 4, we're writing an exponential model when the initial value is known. So how do we go about this? Well, first, we're given two data points. We want to write an exponential model. If one of the data points has the form 0a, then a is the initial value. Using a, we substitute the second point into the equation, f of x equals a b to the x power, and solve for b. If neither of the data points have the form 0a, then you substitute both points into two equations with the form f of x is equal to ab to the x, solving the resulting system of two equations and two unknowns to find a and b. In step 3, we're going to using the a and b found in the steps above, then we're going to write the exponential function in the form f of x, which is equal to a times b to the x power. In example 4, it says in 2006, 80 deer were introduced into a wildlife refuge. I'm going to stop there in that first sentence because I want to make sure that whenever you see how they're starting out with a certain population in a certain year, that's telling you what the initial year is and what the initial population is. So immediately, because A represents the initial value, then the initial population of how many deer there are is 80, and it was in year 2006. In the second sentence, it says by 2012, the population had grown to 180 deer. So what that means is that in 2012, the population had grown to 180 deer. So we're writing n of t because we're using that as our function. So the population n of t represents how much is in 2012, which again is 180. So what it's saying here is that the population was growing exponentially. So we're going to write an algebraic function n of t representing the population n of deer over time t. So again, you look at the first equation, that is our first model of an exponential function. In our second equation, we're just replacing the variable for n and the variable for t. So it's going to be n of t, which is equal to a b to the t power. So again, we know what the initial population was, which is 80. We know that the population in 2012, which is 180. But in this question, they don't give us the growth rate. We don't know what the growth rate is. It hadn't told us that. So B is what we're going to be looking for. But we do know the time. Time is 2012 minus 2006, which is equal to 6. So what that means is we end up with this equation. We get 180, which is equal to 80 times B to the 6th. And then we're going to have to solve for B. So let's reread this again. So we let our independent variable t be the number of years after 2006. Thus, the information given in the problem can be written as input-output pairs. 0, at time 0, the output was 80. In year 6, the output was 180 deer. Now notice that by choosing our input variable to be measured as years after 2006, we have given ourselves the initial value for the function a is equal to 80. We can now substitute the second point into the equation n of t, which is equal to 80b to the t, to find b. So again, we're using that formula, and what we got here now is 180 equals 80b to the 6th. So what we've done is that we're substituting using the point 680 into the function. So the time is 6 and the population is 180. And then what we're going to do is we're going to divide both sides by 180 and then reduce the fraction. So, we divide by 80. So dividing both sides by 80 and reduce the fraction, we end up getting 9 over 4, which is equal to b to the 6th power. And then we're going to isolate b using properties of exponents. So recall that in order to solve that step, if you have 9/4, and that's equal to b to the 6th, you need to multiply both or raise it to the both to 1 over 6. And so you end up with 9 over 4 to the 1 over 6 power, and that's now b. So now we have b, which is equal to the 9/4 to the 1/6 power, and then b is approximately 1.1447 rounded to 4 decimal places. So the growth rate is 1.14, or approximately 114%. Now, unless otherwise stated, do not round any intermediate calculations. Then round the final answer to 4 places for the remainder of the section. So you're not going to round any time until you get to the very end of the problem, is what they're saying. Now, the exponential model for the population of deer is equal to n of t, which is equal to 80, which is the initial population, times the growth rate, which is 1.1447 to the t power. And note that this exponential function models short-term growth. As the inputs gets large, the output will get increasingly larger, so much so that the model may not be useful in the long term. So we can graph our model to observe the population growth of the deer in the refuge over time. Notice that the graph in figure 3 passes through the initial points given in the problem, which was 0, 80, and also it's passing through 6, 180. So we can also see that the domain for this function starts at 0 and goes to positive infinity, and the range starts the value of 80 and goes all the way up to positive infinity.